that, what we do is we slice it. So like when we had our Hershey Kiss, we took a Hershey Kiss and sliced it perpendicular to the axis of rotation, looked at one slice, described the volume of that one slice, and then added up all the slices. Right, so the example that I want to talk about today, the one that I didn't quite get to last class, is we are going to look at the region bounded by y is equal to 4x and y is equal to x cubed in the first quadrant. And we are going to rotate this region about the line x is equal to 2. And then our job is to find the volume of the solid. All right, so there's a ton of stuff going on up here in what I've written down here. So the very first thing I'm going to do is understand what the region looks like. And so if I am not sure what these curves look like, I might graph them on my calculator, but y equals x cubed is not so bad. Y equals x cubed kind of starts down here in quadrant 3, pops up into quadrant 1, and then zips right upwards. So this is y equals x cubed. And then the other equation we have is y equals 4x, which is a diagonal line. And also extends down here into quadrant 3, so this is y is equal to 4x. Okay, so we're only interested in the region in the first quadrant, and so I can actually erase this stuff down here. I don't really care about it, so I'm not even gonna deal with it. And the part of the region that I'm looking at is this kind of half almond-shaped region. All right, are there any questions about that region? Okay. So once I have this region, something that is useful for me is to figure out what the points of intersection are. This one down here is easy. It's right here at the origin. But if I wanted to figure out this other one, then what I might do is to set my two equations equal to each other. 4x is equal to x cubed. And if I want to solve this, then I've got to move everything to one side. So I've got 0 is equal to x cubed minus 4x. And I happen to like algebra and geometry, so I like to solve these things, but if you're not happy about doing that, you can also use your calculator to find the intersection points. Okay, so now I still need to factor this thing, and the easy part of the factoring is that I can factor out an x. That leaves me with x squared minus 4. And then the x squared minus 4 I can factor into, so I've got 0 is equal to x plus 2 times x minus 2. Okay, difference of two squares. And so my three values, I've got x is equal to 0, x plus 2 equals 0, and x minus 2 is equal to 0. So my three intersection points are 0, negative 2, and 2. And two of them I see drawn right here. I've got my origin, my x equals 0. X equals negative 2 is somewhere over here in this third quadrant. I don't care about that one. But the one that I do care about is this point right up here. And so this is x is equal to 2. And if I wanted to know the y value, I may or may not need that, but the y value, I can plug 2 into either of the equations and I get a y value of 8. Right, any questions about our intersection? Okay. All right, so far I've done nothing that has anything to do with rotating around any axes. This is strictly about understanding the region that's going on, which means that so far the question is all about section 7.1. And if we wanted to find the area of this region, then I could put some rectangles in here, and I could add up those rectangles and find the area. But that's not what we're asking for. Here we're asking for finding a volume. So we want to rotate this region about the line x equals 2, which just so happens to be the line that goes through this intersection point up here. So we are interested in taking our region and rotating around the line x equals 2. Okay, so we'll bring this sort of half almond shape out, swing it back into the board over here, and it goes around the back. So take a minute and imagine for yourself what that solid is going to look like. And then try and draw it on your paper.
For a washer with change with respect to y.
So eventually what we'll be thinking about is when we slice, we do want to slice perpendicular to this axis of rotation. Okay, so once you have something drawn on your paper, show that drawing to your neighbor. And if you're not happy with the way it turned out, then explain in words what it is that you're trying to draw on your paper. Yeah, I know. Okay, so does anybody have what they feel like is a good description of what this solid looks like? Like if somebody just walked into this room and was like, "Hey guys, what class is this? What are you talking about?" And you're like, "Oh, well, we're talking about these solids, and here's what it looks like." How would you explain it?
Let's say a hollow cone.
Hollow cone? Okay. So that seems reasonable. Our outside is flat, at least, and so that's going to spin around. So the outside is going to be looking just like an upside down cone. Okay. So just sort of trying to get a sense of what the picture looks like. Here is our outside part. Okay. And when you talk about a hollow cone, can you talk about anything else that goes along with your hollow part, like the inside part?
Is a circle inside?
What's that?
I guess like a washer inside that's getting, I guess the circle is getting bigger and bigger.
The circle is getting bigger. Oh, from the top down?
Yeah, from the inside. When it comes out.
Okay, so not totally hollow, not like an ice cream cone where we just have the outer rim of it, but we do have some stuff inside as well. And so, for example, if I try and draw an inside portion to this,
It has a convex cross section.
convex cross section. So what do you mean? Which part of your cross section?
Well, you know, if you peered it from a three-dimensional perspective, if you're peering into the cone, you've already drawn it. So that shape has a convex. When we look at it in for example, when we look at it in 2D, we're looking at the cross section right there.
Okay.
So the wall of the cone has that convex, convex being convex shape on the inside of the cone.
All right, so yeah, so this thing here is, and I saw a lot of people doing this with their hands. And so that's a pretty good description of what's happening on the inside. So the inside is not flat walls, the inside is poofing out, kind of. I mean, it's convex on the inside. Now, okay, so here's an example of a picture of what the solid might look like. Okay, now, in my opinion, it's a good idea to have two separate drawings. One is a drawing of what the solid is going to look like, and or a description of what the solid is going to look like, and then also have a working diagram. Okay? So over here, what we have is sort of my two-dimensional slice of this thing. That would be if I just took the solid and just went whack and sliced it down the middle. Alright, so this is my working diagram over there. I've got what my solid actually looks like. Yes?
So do we find the radius and then go 2 minus one way and 2 plus the other way?
So let's see if we can figure out what's happening here. Okay, so you're on the right track, but let's make sure everyone's got what's going on. So here we've got our picture. We always slice for washers and discs, we always slice perpendicular to our axis of rotation. So in this case, what we're doing here is slicing parallel to the floor, slice, 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 slice. The very top slice is very, very, very small. The very bottom slice is very large, but has a very large hole in the middle as well. So a typical slice is going to look something like this. And it will be a washer because we have a hole in the middle. Alright, so as soon as I know what a typical slice looks like, I want to talk about the volume of one of these washers. And the volume, which we talked about last time, is pi times big R squared minus little r squared times the thickness of the washer. Or the height of the washer, if you want to describe it like that. Alright, so I'm going to use my working diagram to actually talk about the 2 radii. When I talk about the thickness, I can see from my real picture over here that the thickness is a little bit in the y direction. Okay? And so my thickness will be dy. And I always want to make that choice first. What's up?
It's not dx?
So when I look at this little distance right here,
Oh, yeah.
it's a little bit in the up and down direction, so it's a dy. Okay, so as soon as I make that decision, and this decision right here determines an awful lot about the problem. As soon as I make that choice, I need to go back to my equations and say, okay, I do not want y equals x cubed. What I really want is to solve for x. And so rather than y equals x cubed, I really want x is equal to the cube root of y. And rather than y equals 4x, what I really want is x is equal to 1/4 y. So I want to use the equations where I have the functions in terms of y because I've made this choice for my thickness to be dy. Okay, so next thing we want to talk about are the 2 radii. Okay, so we've got our capital R and our little r. And here's where I want to look at both of my diagrams. Now, my radius, my large radius, is going to go from the center of the washer out to the edge. It doesn't matter which edge I go to on this picture, but when I'm looking at my working diagram, what I want to think about is where will my radius show up here? And I want my radius to be drawn so that it uses the original region that we have drawn. So even though I could draw my radius out to the right, because the true region is this shaded one over here, I'm going to draw my capital R radius so that it is involved with the original region. So this is my capital R. We are officially out of colored chalk. What's that? Okay, so are there questions about drawing this capital R radius here? I'm also going to have a small radius, which will be the distance from my axis of rotation out to the inside wall. And so that's my little r. Alright, so let's take a look at our big radius. And what I notice is that this radius is not going to the y-axis. So this radius here is kind of like when we had horizontal rectangles that were bound between 2 curves. So to get this distance for r, what I want to think about is top minus bottom. Now we have sideways rectangles, so top is really to the right. So I can kind of turn my head on the side and look at it like this and say, okay, the top of this radius strip here is on x equals 2, and the bottom is on the straight line. So my top is 2, and my bottom is 1/4 y. All right, are there any questions about writing that part down? Okay. Our little radius, when I'm looking at that, again, I have to turn sideways here, and top means over to the right. And so my top of the little radius is on x equals 2, and the bottom is on the curve, the y equals x cubed, but I need to write it as cube root of y. So we have 2 minus the cube root of y. Okay, so these are our 2 radii. So one thing to think about is, think about if instead of rotating around x equal to 2, if we had rotated around the x-axis, then our radii would be different. Around the x-axis, we'd be swinging, the y-axis, we'd be swinging around this direction. First of all, the large radius and the small radius would be switched, and we wouldn't have this 2 minus part involved with it. Okay, it would just be the name of the function. Okay, so here's all of our information. Big R, little r, and dy. And so the volume of one washer is going to be pi times 2 minus 1/4 y squared minus little r, 2 minus cube root of y squared, and then a dy at the end. That's the volume of one washer. So last but not least, now that we've figured out the volume of exactly one of these washers, one of these typical slices, we now want to add up all of those slices. So we want to add up those slices starting at our lowest y value, which in this case occurs right down here at y equals 0, and we're going to slice, 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 slice. The very last slice is going to be right here at the tip, which occurs at a y value of 8. So we're going to add up all the slices starting at 0 and ending at 8, and we're adding up pi times 2 minus 1/4 y squared minus 2 minus the cubed root of y squared, and then we have a dy here.
And how did we get that 8 again?
This 8 right up here, the way that I came up with that is I was looking, so earlier on when we had figured out the region here, we figured out that the x intersection point was x equal to 2.
Mm-hmm.
And so when x equals 2, the y value of this function is...
Also just 2 cubed.
Yep, 2 cubed. And it would also work to plug it in for 4 times 2.
Okay.
And it should work in both of them. Okay, so we now have an integral which describes the total volume of this solid with the funky convex inside. Any questions about that? Okay, what would be our very first step if we wanted to evaluate this integral?
The pi in front.
Okay, pi in front, what's our next step?
FOIL out our 2 R's.
Yeah, so pull that pi in the front and then FOIL out these 2 guys and then do some simplifying and do your antiderivatives. Okay. Alright, so we're not going to focus on that part today. Today I want to focus mainly on setting up, and I'll let you guys work on the solving part on your own. Right, Mike.
So the reason that you changed the x to y value is because you're
So the reason that I changed and used the y values as opposed to, say, 2 minus x squared here, or x cubed there, is because our thickness choice was dy. And if I want to talk about an integral that has a dy at the end, then every variable on the inside has to have a matching variable with the one at the end. And so I was being preemptive about making sure that my integral made sense. Okay, so whatever this letter is here at the end, your boundary is going to be in that same variable, so these are y boundaries, and everything in between has to be in terms of that same variable as well.
So what if you kept a dx?
So if we had, for example, if we wanted to use a dx, then our slices actually would have been vertical, because that choice that we make is the choice of dy or dx depends on the way that the slice is oriented. And so that thickness, because that thickness is a little bit in the up and down direction, that's why we have to choose dy.
So if it was turned that way, you put it that way.
So if instead, if I were rotating around a different axis, if for example I was rotating around y equals 8, then I would have slices that were in this direction and have a little thickness which is dx. And then I would keep the equation y equals 4x and y equals x cubed. Does that make sense?
So you would still change your y value? Or, yeah, you did.
What's up?
Yeah, you did.
You're good?
Yeah.
Y is equal to 1. y equals 2, x equals 0, and we are going to rotate about the y-axis. And our directions are to find the volume of this solid rotated about the specified line, in this case about the y-axis. Okay, so this is an even number problem, which means there's one answer in the back. What were your first thoughts on this one?
I got my picture.
Okay.
I'm stuck on the fact there's no right-handed bound.
Okay, so let's look a little more closely at the picture. So very first thing that I want to draw is y equals natural log of x. Here it is. And in terms of natural log of x, I know that natural log of x crosses the x-axis at x is equal to 1. And some other information here, we've got x is equal to 0, so this is our vertical line here. We have y is equal to 1. And we have y is equal to 2. So is that about what your picture looks like? Okay, great. So one thing I want to caution you on in this is that not only do we have our 4 curves that are described and told to us to draw in here, but we also have our y-axis and our x-axis. And so when I look at this, I have to be careful because there are actually 2 regions that I could color in. And I want to be careful to choose the correct one. And the correct one is going to be the one where our left-hand side is bounded by x equal to 0. The right-hand side is bounded by y equals natural log of x. The top is y equals 2, and the bottom is y equals 1. This one down here doesn't work because technically these are just the axes. They're not actually lines that we've drawn in there. And so this is not really a region that we're looking at.
I can finish it now.
So you're good from there?
Mm-hmm.
Okay, so once we have this picture, then we are going to rotate around the y-axis, which is around this direction.
I do have a question though. So why is it not under the curve? That was my problem. I was looking for an area under the curve to shade in and not above it. And
Okay.
I had no right-hand x bound, so I didn't know what to do. Why is it?
So whenever we're given a bunch of different curves, when you're given just one function, there it is, then typically we talk about area below the function and above the x-axis. But when we're talking about finding a region that is bounded by curves, that doesn't tell us necessarily that we're looking below or above a particular curve. It's whatever these guys are the edges of.
Okay, that makes sense. That's where I was stuck.
Okay, cool. All right, so unless somebody wants me to continue, I will leave that here.
Just to kind of draw the 3D model of it maybe,
Okay.
please.
All right, so the 3D model, we're going to rotate around the y-axis. So this piece is going to pop out of the board, pop in the board over here. So my working model, well, that's my working model. My actual attempt at a 3-dimensional drawing. Well, the top and the bottom are still going to be totally flat. And so I'm going to end up with a circular flat piece on the top. My edges are going to curve in. And then I'm going to have a circular flat piece on the bottom as well. And so, totally solid. Okay. There's no hollow part on the inside. Flat on top, flat on bottom, and it sort of grows out almost like a vase on the outside. Okay, so that is our picture. Any questions about that? Okay. All right, so I'm going to go ahead and set up the washer or the slice to see what's going on. So now, when I look at this, here's my axis of rotation around the center. And so when I slice, I'm slicing perpendicular to that axis of rotation. And so one slice is going to look something like this. Now on the board that looks like a ring, an outside just a ring, but it's a solid disc. I drew on the edges of that solid disc, but we have a solid disc. There is no hole in the middle because our region goes right up to and hits our axis of rotation. And so we want to look at the volume of one washer, one disc, which is pi r squared times the height or times the thickness.
It's dy.
And in this case it's going to be dy. And I can see that from the picture because our thickness is a little bit in the up and down direction in the y direction. So the thickness is dy. As soon as I write down that thickness, because that thickness is in terms of y, I need to go back to my picture over here and say, okay, everything needs to be in terms of y's. So, for example, y equals natural log of x. I need to solve that equation for x.
So just add e.
So I'm going to have to hit both sides with e, so I've got e to the y is e to the natural log of x. The e and the natural log cancel, and leaves me with x is equal to e to the y. So this curve right here, which was y equals natural log of x, I can also think of that as x equals e to the y. So now my radius, when I look at the radius here, I'm looking at the distance from the center of the disk out to the edge, which in this picture goes from the y-axis out to our curve out here, which is y equals natural log of x. Now, if I were the last problem we did, we had to think really hard about this, and so I'm going to think hard about this even though I don't have to. When I turn on my side here, and I look at this radius that I've drawn, the top of it is on the curve e to the y, and the bottom is on the curve 0. So it's really e to the y minus 0, top minus bottom, but I don't need to worry about that minus 0 part. So our radius is strictly e to the y.
Squared.
Well, the radius itself is just e to the y. So now, once I put this into my volume of one disk, then I have pi times e to the y squared times dx.
And then your limits are just from 1 to 2.
And now when I'm
dy,
slicing,
isn't it?
our y values are going to go from y equals 1, slice, 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 up to y equals 2.
dy, isn't it?
Yes, thank you, dy. And so our total volume, we're going to add up all those slices. The bottom slice starts at y equals 1, and our top is at y equals 2. And so we have pi e to the y squared. I'm going to simplify that to e to the 2y, and then dy at the end.
Nice. Got it.
All right, so now we've set up our integral. If we wanted to solve this, we would pull the pi out in front, and then I'd have e to the 2y, and I might do a u substitution on that, or if I've done enough of them, then I know what the antiderivative of e to the 2y is. But if I wasn't sure, I could do a u sub on this one. All right, questions or comments on that? Going once? Going twice? Okay. All right, so here's our example. We've got y is equal to 1 over x is equal to 1, x is equal to 2, y is equal to 0, and we'd like to rotate about the y-axis. So we're going to take this region and we're going to rotate it about the y-axis. And we'd like to find the volume of the solid. Okay, so very first thing that I want to do is understand what this region looks like, the region bounded by these 4 curves. 3 of these curves are easy. I've got 2 vertical lines and a horizontal line. The most interesting one is y equals 1 over x, so I'm going to draw that one first. And so we've got y is equal to 1 over x, and technically y equals 1 over x is in 2 separate quadrants. I've got x is equal to 1, x is equal to 2, and y is equal to 0. Okay, so these are all the curves that I'm given, and even though I have part of y equals 1 over x over here in the third quadrant, that portion doesn't help to block off any specific region. So I'm not even going to worry about this part over here in quadrant 3. I can just go ahead and erase that. And it looks like the region that we're interested in is this region right here where the top of it is 1 over x, the bottom is y equals 0, and then the left and the right are x equals 1 and x equals 2. All right, so there's our region. Any questions about the region itself? Okay. So we now want to take this region and rotate about the y-axis. So we're rotating around the vertical axis. And so when I think about this thing, I'm going to be taking this region, pulling it out of the wall, swinging back in over here in quadrant 2, and swinging around the back. And so in my head, what I'm imagining is this object that has a hole directly through the center. Around the outside, on the bottom part, we've got round and flat, and then almost like a circus tent kind of coming up across the top. So here's my attempt at drawing this. Here's the center. And then the outside pops out. And so we have this thing that is flat and vertical on the outside until it sort of swings up to a little smokestack on the top, hollow in the middle, but otherwise solid. Okay, so our method of madness, our method for figuring out the volume of a solid like this is going to be to slice this thing perpendicular to its axis of rotation. And so we're going to get washers, okay? And because our washer will have, well, let's see here, if I add on to my working diagram here, I've got my mirror image picture over here. Try to make it as mirror as possible. And so one washer might look something like, well, here's my inside, and then here is the outside. And so I've got one washer going on there. Now notice what happens though. If I'm slicing this thing, and I'm slicing, my top washer up here, I've got an outside radius that goes from the y-axis out to 1 over x, and an inside radius that goes from the y-axis out to x equal to 1. But if I continue to slice, look what happens here. Down in the bottom, my washer changes. My washer changes so that the inside radius is still the same, but the outside radius is going to be on a different curve, which means that if I want to set up the volume for this thing, I'm going to need to set up two separate integrals. And so my first integral is going to be an integral that maybe if I'm looking at this top part, let's see here, I'm going to have, for the top, I'll have a thickness, which is dy, which immediately means that I need to resolve all of my equations. Y equals 1 over x is the same as x equals 1 over y. That's the only one I need to worry about. My outside radius, my large radius, is 1 over y. My inside radius, this one right in here, goes from 0 out to x equals 1, so my inside radius is 1. And so my first integral will be the integral of pi times big R squared minus little r squared times our thickness of dy. And so we'll have the integral of pi times 1 over y squared minus 1 squared dy. And for that top part up here, when I'm looking at that part, I've got to start somewhere and I've got to end somewhere. So how do I know where to start and end? Yeah, the intersection of y equals 1 over x with x equal to 2. This point right here is x equal to 2, but we need the y value for that. And so when x equals 2, y is going to be equal to 1/2. And so our bottom boundary of this one is y equals 1/2. And our top boundary, we're going to slice, 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 slice until we hit the place where 1 over x hits x equal to 1. And so when x is equal to 1, our y value at that point is also 1. And I get that one up there by saying when x equals 1, the y value of 1 over x is 1 over 1, which is 1. So my boundaries go from 1/2 to 1. All right, are there any questions on that integral? That is the integral strictly for the top part, the part that almost looks a little bit like a circus tent. Okay, so that's our first part. The other part that we need is the volume along the bottom. And so those slices that we look at down here, down below on this part where the outside radius is now different, in that bottom part, our thickness, again, will be dy. But our outside radius, when I draw my washer down on this bottom part, my outside radius goes all the way out to x equal to 2. And so my radius goes from 0 out to 2. So my large radius is 2. My small radius is 1. Are there any questions on either of these two radii?
We really don't need to do an integral for that, right? It's just a flat, yes.
That's right. So for this particular one, the integral is kind of boring. And you could do it straightforward with, here's my cylinder, subtract the outside cylinder minus the inside cylinder. Absolutely. But if I did want to set up the integral, then my final interest here would be the integral of pi times big R squared, so 2 squared, minus little r squared, 1 squared, dy. And I'd be starting by starting at a y value of 0, slice, 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 until I hit y equals 1/2. Because at y equals 1/2, that's when I switch over to the other type of washers. So we go from 0 to 1/2. And so that's the bottom half of our solid, which means that our total volume is going to look like the integral from 0 to 1/2 of pi times 4 minus 1 dy, plus the integral from 1/2 up to 1 of pi times 1 over y squared minus 1 dy. And so I would now have to go ahead and integrate everything and plug in my boundaries and come up with a final answer. Okay, so are there questions on setting that up?
So just on to set up the top part, to find your boundary, all you did was just plug in your 2 to the equation?
Yes, so if I want to figure out this intersection point here, then what I want to know is when x is equal to 2, what is the y value at this point? And because the x equals 2 line intersects 1 over x, I can plug in 2 for x, and that would be my y value. If it's two fancy curves, then I might set those two curves equal to each other.
And you got one because all you do is just plug in 1, 2.
Yeah, I plug in one into one over x. Okay, so before you head off on your break, I want to give you a thought to think about here. If I take this picture, the original picture that we had, and I draw the region that we were interested in, here it is, the original region before we rotated around the y-axis. If I asked you to find the area of this region, would you prefer to look at horizontal rectangles or vertical rectangles? Yeah, vertical rectangles actually make way more sense here. And the reason that a vertical rectangle makes sense is because whether that vertical rectangle is all the way here on the left or all the way over here on the right or anywhere in the middle, no matter what that vertical rectangle, the top is always on the curve, y equals 1 over x, and the bottom is always on 0. So I don't actually have to split this up into two separate integrals. And so this region is more naturally set up to talk about vertical rectangles. Now, when I sliced perpendicular here, that gave us horizontal strips. And that's what was a bummer here, is that we had to split up into two separate integrals. So as you're going out and grabbing a water break or doing whatever you're going to do over the break, think about what this vertical strip is going to look like when we take this region, rotate around the y-axis. It's going to give us a shape that's going to be different from a washer or a disc. So think about what that shape will look like, and I'll see you in 10 minutes. I want to think about the idea of, what if we start with a vertical rectangle inside of this region? And so here's our picture. If I draw one vertical rectangle, very skinny, remember these rectangles, in terms of the Riemann sum, they have a width to them, but eventually we're going to make that width get as skinny as possible. If I take this vertical strip and I pull it out of the board and rotate around the y-axis and bring it back into the board over here on the left side and then around the back, the shape that I'm going to get is going to be, essentially it's going to look kind of like a cylinder, a vertical cylinder. It's going to have very, very skinny walls. There's going to be no top on it, no bottom. Essentially it's going to look like a soup can with the top and the bottom of the soup can cut off. And so this object, this vertical rectangle, when I rotate it around, is going to give me an object that looks like this cylinder. Now it's just the outside shell of the cylinder, and so sometimes these things are called shells. And the wall of the shell, the wall of the soup can, has a little bit of a thickness to it. And so that's one shell. Now, if you imagine what's happening here, when I take this solid and I swing it around, each of these vertical rectangles is going to create a separate shell. And so essentially what I have is, I'm going to have a bunch of nested soup cans. So if I try and draw this thing, to give you an idea of what this three-dimensional thing looks like, here is our original region. We have the mirror image on the other side. One shell will pop out of the board, it'll pop in over here in its mirror image. And so we have one shell. Now, the next rectangle out, the next rectangle to the right is going to swing around the outside of this shell, and so it's surrounding it, and it's a little bit shorter. And then we have another one that's even farther out, so here's another shell. where we've got the two sides on it. And we have a really tall one right here in the middle. And so we have a whole bunch of these soup cans. Some are skinnier than others and taller, and others are shorter and wider. But in the end, we have a bunch of these nested soup cans. And the idea is that when we put all those soup cans together, then they create this solid that we're looking at, the solid that we talked about a little bit earlier. And so rather than thinking about slicing and putting a bunch of discs or washers stacked on each other, we're going to think of breaking this up into these nested shells. And so if we can figure out the volume of one of these nested shells and describe that, then we can add up all the shells starting in a certain place and ending in a certain place, and we've come up with the volume of this object in a different way. So thinking about this shell. These cylindrical shells, this one that I've drawn over here, which I'll call it shell, or more technically cylindrical shell, aka soup can. Before we go further, are there any questions about visualizing these shells, these nested soup cans? Okay. All right. So our goal is going to be to find the volume of one of these soup cans, one of these cylindrical shells, and then use that as our standard shell, and then add up all the volumes.
I do have a quick question. Okay, so you're breaking this up. I mean, they're going to be hollow like in the center where it's not hitting the y-axis, but then are they hollow also between?
So there are actually set meaning between, like, for example, this one and this one here. So there are probably more of these that there's one that's snug right up against this wall, and then snug up against the next one. So I've only drawn the equivalent of maybe, it's like I've drawn these three rectangles on the original picture. There are also rectangles in between those, I just haven't drawn them.
Well, but then I mean, like from that one, like the tallest one there.
Yes.
Between there and then the outside line of the shape.
Yes. So from here to here?
No, just from, yeah.
Yes.
That little wedge.
Mm-hmm.
I mean, it'll be full of other rectangles, but without taking those other rectangles, is that piece then?
So I also have, I have a rectangle that's right up against the inside wall of my shape, and that corresponds to a rectangle right here. And so I've got my innermost shell is the one that creates the inside tube on our original solid.
So all of these are only hollow then still without the y-axis and not really different?
I'm not sure I quite understand what you're asking.
Well, like that center piece between x equals 1 and x equals -1.
Yes.
That's going to be the only really like empty space, I guess.
Yes.
And the rest of it's going to be full of all these random rectangles.
Shells, yes. Yes. So yes, so from here to here we have rectangle, 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 all full all the way up to the edge. And that corresponds to shell, 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 shell. Okay?
Why can't we take the area of our original graph right there
Mm-hmm.
and then spin that around 360 degrees? You know what I mean?
So
Like take the integral from 0 to 2 pi of that.
So part of the issue there is that if I have, so if I take this picture and I instead have the same picture still going from 1 to 2, notice that when I rotate this guy around, my solid is going to be much different in the sense that now the heavy stuff is out on the outer part. So even though I might have the same exact shaped region, the way that it's oriented and the way that it's rotated will change my volume. And so I really do have, the two things that go into your volume are the radius, the distance away, as well as the amount that we have. And so because those two things are both changing, we have to break it up into smaller pieces so that we can take into account both of those changes at the same time. Does that kind of make sense?
Yeah.
Okay. Other questions or comments? Okay, so let's figure out the volume of this cylindrical shell. So here's what I'm going to do. If I had a pair of very, very strong scissors, I would take the board and I would cut it. And I'm going to take this cylinder, or my soup can, I'm going to cut it up one side, and I'm going to peel it open. So that this guy, here we go, it doesn't really matter where I slice it, I'm just going to cut it right there, and I'm going to open it up. And when I open it up, it's going to give me a rectangular piece with a little bit of thickness to it. So it's this slab, very skinny slab, that was my metal can that is now opened up into a rectangle. Now the volume of this piece of metal that I have here, well, volume, because this is a nice rectangular slab, is length times width times height. And so here I've got a little bit of distance, which I'll call my thickness. And then I've got my height. And my width, well, that width on this slab, remember where this slab came from. It came from, if I wrap it back up, it was the circumference on my shell.
2 pi r diameter of a tube, right?
So I'm not really sure what my diameter is precisely, because each of these shells actually has a different radius on here. But if I describe this shell with a radius of r, then the circumference of that is going to be our 2 pi r. So I now have the 3 different dimensions on this slab. Are there any questions about where those dimensions come from? Either the height, the thickness, or 2 pi r, which is the circumference of my shell. Okay? Alright, so what that tells us is, since the volume of any kind of a slab like that is length times width times height, then we can conclude that the volume of one shell is going to be 2 pi r times the height times the thickness. And so if we want to come up with our total volume of our object, then we'll take the volume of one slice, 2 pi r times the height times the thickness, and then we'll do the same thing for every single shell. We'll add up all those shells, starting at some place and ending at some place. So starting at A and ending at B. All right, so let's look at it in terms of our example. In our example, we have our picture of our original region. And we had x equals 1 and x is equal to 2, and we have y is equal to 1 over x as the curve across the top. And we're talking about a shell which starts with a vertical rectangle. That vertical rectangle swings out and pops back into the other side. And here's our sample shell. So in terms of our sample shell, what we have here is we've got a radius, which goes from our axis of rotation out to the wall of the shell. We've got a height, which is the height of the rectangle. And we've got a thickness, which is the thickness of the wall, which is the width of our rectangle. Alright, so are there any questions about the labels that I have drawn on here? The radius goes from the axis of rotation out to the wall of the shell. Okay. So now we want to write down the volume of this one shell for this particular example. And so we'll start with our thickness. That's always where we want to start. Our thickness is the width of our wall, which is a little bit in the x direction. And so our thickness is dx. And that information tells us that everything else should be y equals stuff in terms of x, so we don't need to resolve anything, and that's good. Our height, well, the height of this wall, whether I'm looking at an inside shell here or a very wide shell, no matter what, that height goes between the function 1 over x and 0. And so our height is 1 over x, or if you want to think of it as top minus bottom, it's 1 over x minus 0. And our last value is the radius. And this is the one that's a little bit strange, so I want you to kind of think about this one a little bit. But the radius goes from the y-axis out to the wall of the shell. So we are looking at the distance from x equals 0 out to whatever x value our wall lies on. So the distance from the y-axis out to our sample x value is a distance of x. And so our radius is equal to x. So, for example, at our very skinniest shell here, the radius is 1, which is the x value of the wall. And for our very fattest shell, the radius is 2, which is the x value of the outside wall.
Do we need to put boundaries on that radius then? Or it should be like greater than equal to 1?
So that's where our bounds, that's where the a and the b are going to come in. So for now, this is just our x value. Okay?
So the radius is just the distance from the point of rotation to the particular shell we're talking about?
That's correct.
Okay.
That is correct. And so if we are rotating around a different, something other than the x-axis, or I'm sorry, something other than the y-axis, then this distance from the y-axis to the wall is still a distance of x, but if we're rotating maybe this way, then we'd have to figure out what this distance is. Okay, other questions about thickness, height, or r? Alright, so that tells us that the volume of one shell is going to be 2 pi r, so 2 pi times x, 2 pi r times the height, which is 1 over x, times the thickness, which is dx. And that tells us then that we can set up our total volume. And so our total volume will be adding up all of the 2 pi x times 1 over x dx's. And we're going to add all of those up. Now when I'm thinking about adding up these shells, I want to think about, okay, how do these shells work in terms of my initial region over here? And my standard region that I started with, the innermost rectangle, the innermost shell, has an x value of 1. And I'm going to start adding those shells, add, until my last shell has its wall out here at x equals 2. So my boundaries will go from 1 up to 2. And so now I have an integral which describes the volume of our solid. And if I was super excited about this, and I kind of am, then I might go ahead and solve this. And so if I want to solve this integral, step number 1, I'm going to pull the 2 pi out in front, and then I'm going to clean up x times 1 over x, which simplifies to a 1. So I've got 2 pi times the integral from 1 to 2 of 1 dx.
So 2 pi half x squared for 1 and 2.
So yeah, now I'm going to take my antiderivative of 1, which is just x. I'm going to evaluate that between 1 and 2, so I'll plug in 2, and then I'll plug in 1, and I'll subtract them. And so I end up with 2 pi times 1, which is 2 pi. And I'd like you to contrast that calculus work right there to the work that we would have had to do to solve the prior 2 integrals that we had to add together. And those were not quite as easy. Okay, so 2 pi cubic roots. And I would encourage you to check the 2 previous integrals that we set up and see that you also get 2 pi, but you'll have to do a little bit more work to get there. Okay, are there any questions about this one? This is an example of a volume using cylindrical shells.
So this equation is gonna equal 2 pi, 2, is that what you're saying?
That long integral where you had